Now, let's move on to the next presentation, which is about the twin systems, the end of the beginning, and overview of the digital twins life cycle for the built environment. So let's welcome to the stage Senior Research Associate from the Department of Engineering, University of Cambridge, Dr. Erika Pärn.
There we go. That's the right height. Good afternoon, everyone. So thanks to the organizer. I'm in the graveyard slot, but I'm going to try and keep this interactive so that we stay awake still within this afternoon slot. So twin systems, the end of the beginning. This is actually the title of our upcoming book that I'm writing together with my colleagues from Cambridge and across the world. And today's presentation will give you an overview of how we think about the digital twins life cycle, how our built environment professionals can come to think about it in terms of a life cycle, much like we do already understand the physical assets have their own life cycle as well. So the title of my presentation is the same as our upcoming book. It's been taking a while to get this together, and we've just been sort of delaying because you can imagine doing a PhD is difficult enough, but writing a book with 4 other professors is even more challenging. So it's taken us a while, but we're hoping to release it in December of this year. But if you want to know more about the contents of our book and really the dialogues and the debates that we've had, you can have a look at our YouTube channel where we have short snippets of some of the key ideas and concepts we introduce in our book. It's work that's been co-authored by Professor Ioannis Berlakis from Cambridge, Professor Mark Enzer, also from Cambridge, Professor Rafal Sachs from Technion, and Professor Lucio Soibelman from California. And this initiative was really to try and put together a book similar to the BIM handbook. I don't know if any of you have ever read the BIM handbook, but this was work that Rafal Sachs led. And we wanted to come together and do something of a similar ilk, but on digital twins for the built environment. Now, how do we define or talk about digital twins? Just like everybody else in today's presentations has their own interpretation and understanding of what a digital twin is, so do we. And it took us a while, really, to come together to a conclusion of what do we want to call this? And for us, it's a systems approach. And therefore, we've narrowed down our scope to this one terminology, the twin system. And if we have a digital twin, it ultimately has to have a physical counterpart as well, and that's what we call the physical twin realm. And that in itself, the way that we describe it, is composed of 2 parts in both realms, both the product data and the process data. In the digital twin, we will have certain product data and process data, and in the physical realm, we have product and process physical things. So when I say product physical twin, I'm talking about the physical floor slab. When we say the physical process, we're talking about the activity of laying that floor slab. And in the same realm, in the digital twin side, we're talking about digital twin processes. So this might be the information related to constructing that floor slab, laying the concrete, and its representation in a 3D environment. Ultimately, both sides will kind of deliver a different type of output or outcome. Ideally, we want knowledge from our digital twin side. But the reality is, just like we've seen today, we're sort of drowning in data, but we're starving for knowledge. We haven't got that knowledge stage yet. It's something that we're trying to achieve within the built environment through the use of twin systems. This is our definition of a twin system, and the main difference here between just the concept of a digital twin is that we split this into 2 core domains, products and processes. This is a more flexible framework in our opinion, because you don't necessarily have to twin a physical asset on its own. It may be a twinning of a behavior, of an activity, a process on site. This is something to help us achieve digital twinning, not just of the physical assets themselves, but the processes that interrelate with it. So the critical component here is having a systems framework. The built environment is a system of systems, and so too will the digital twin eventually be a system of its own. And just like the previous speaker talked about the digital, the social, and the physical realms, well, the more we develop in these domains, the more we increase complexity. And to better understand their relationships, we adopt a systems approach to thinking about digital twins. As I mentioned, the twin systems is a more flexible way of defining or understanding simply what is a twin. It's a more inclusive framework, we feel. And if you remember, much like how BIM was talked about in the past in terms of levels, we don't see that there's an equivalent with digital twins. We almost see that digital twins kind of begin already at the design stages and can be used at different life cycle stages of the development of that built asset. So this is a visualization of the life cycle of the digital twin. At the top, you're seeing the physical twin products and processes over time. This is a very typical standard structure: the design, the construction phase, and then the operation phase. At the bottom, you see the counterpart of the digital twin product. So the best analogy we come up with is actually similar to human development. If you think about the early design stages, this is where the digital twin starts to take form. This is sort of the birth of the digital twin. As you continue and move on towards the construction stages, you will again be incorporating construction phase related product data and process data. And as you mature towards adulthood, or when the asset is in operation, you are now combining multiple streams of product and process related data that relate to the digital twin. And as you see the axis going from up to down, this is just demonstrating the increase of information streams throughout the life cycle stages. But an important distinction needs to be made here. So if you think about the physical twin, and if we use the analogy of a human and its development, it reaches an end. Ultimately, a project may be demolished and it reaches a finish in the physical world. But a digital twin representation of that asset doesn't necessarily die off. It is something that can continue to provide value and knowledge towards stakeholders, even after the project has come to an end or is being demolished. So that is a distinction between the digital twin lifecycle and the physical asset lifecycle. It's not necessarily linear in the same sense. It has an opportunity to be capitalized and utilized even after the asset is demolished and comes to its eventual end. Within our CIT lab at the Civil Engineering Department, we have lots of researchers. We have over 50 researchers looking at digital twins across different life cycle stages. We have researchers focusing on mobile mapping, laser scanning, constructing the digital twin, and then designing the digital twin. The small group of researchers that I'm leading focus on digital twins at the operation stages, where we assume that a twin is already in existence. So we have various different areas that our researchers cover. So Dr. Sun is looking at structural health monitoring or capturing of roads conditions and digitally twinning the structural current condition. We have Dr. Hamid Reza, who's working on Project Omicron, which focuses on the decision support systems, mainly for road maintenance. And we have Dr. Sohaila. Her research work is actually part of my own research project, which is focusing on generative design tools that utilize digital twin data. So this is where we already assume we have a digital twin, and we can utilize some of that information into the next design of structural steel frame components. And then finally, my PhD student, Hank, he's looking at interaction with digital twins, which is a key component of actually unlocking a lot of these solutions that we've seen today. Because as many of you have seen, there's lots of different platforms, software solutions, but there's no one key natural way for us to interact or retrieve some of that information from the digital twins. And if we can incorporate a more natural way to interact with digital twins, then there's a potential to now harness information from multiple sources of digital twins, whether it's for roads or buildings or other public assets. So an example of how Hank's work is covering interaction with digital twins, he's developing at the moment a large language model-based natural language interaction with digital twins of roads. So our road asset operators, and that's mainly Highways England, who are co-sponsoring our research, are looking to utilize multiple sources of data or streams of information about the current conditions of roads, traffic data, etc. But one key part to unlocking that is actually making it usable, because most of the tools, as we all know, currently on the market require a lot of specialist training. They're not the most user-friendly. They're inaccessible to most maintenance workers in our sector. So there needs to be a way to bridge or unlock accessibility of that information to our stakeholders. And one such way is to enhance the way we interact with that information. So that's what Hank's project is doing, is essentially incorporating a large language model-based interface so that you can have a dialogue with your twin, essentially. So in this case, there's use cases for road asset owners, but really it does have potential implications to many other stakeholders. For policymakers, for the general public, it can mean that we can improve our consultation periods where the general public can have a natural discourse with the information. So there are some other areas that we want to enhance with this tool case. So we currently have 5 tasks that the chat twin can actually use within our proof of concept, but we want to actually increase the tasks, and we want to make this interface task agnostic, so it can interpret virtually any task you ask of it within that digital twin platform. We want to enhance into multi-turn interactions with the twin so that you can have a longer dialogue with the digital twin platform and actually have a sort of sequence of consecutive requests with the chat interface. And we're conducting user studies and comparing how this interaction might be better than the traditional graphical user interfaces that we currently have within digital twin platforms. Here's a quick video. I hope this works. There we go. This will show a quick demo of some of Hank's interactions on Chat Twin and those 5 key elements. And thanks to actually Tallinn City Council, we were able to develop some of these interactions just by virtue of them sharing that data for us to use. So there's 5 key tasks it can currently handle. So data visualization, data summarization, and perform minimal changes to the semantic data of the digital twin. Data visualization can be produced with a chat interface, data summarization with that particular digital twin model, and applying direct modifications to certain parameters of the digital twin, as well as visualizing segments of that digital twin through a chat-based request. Now, we have been using the OpenAI large language model, but we're actually training the model to understand multimodal feeds of data, so geometric and semantic data, as well as things like work schedule inquiries, or even helping us create revisions to the existing work schedules. So that's just one example of the type of research that we have been developing in terms of interaction with the digital twin itself. Another area that Soheila is looking at is part of Project Restore. Now, the idea of Project Restore is actually to combine lab-based non-destructive testing of steel frame components and simulation data to create a catalog or a library of steel frame members that can then be used to generate new designs of industrial buildings. The idea is to actually be able to reuse structural steel components rather than go through the recycling process. So part and parcel of her work is the generative design element. So taking these existing steel frame members from a catalog and then assigning them to the new design, where we are reusing the steel frame rather than going through the recycling process. And this is a collaborative project with the University of Birmingham as well. It's gotten funding through EPSRC. It's about 1.3 million pounds of funding, and there's a collective team of us from both Cambridge and Birmingham. So this will just do a quick demo as well of some of the generative design tools that she has developed so far. So as I mentioned, 15%, less than 15% of structural steel frames are reused. Most of it is recycled. So the premise of our work is actually enabling circular principles of reuse of steel frame components by combining simulation data and also non-destructive lab-based testing data. This is then fed into a generative design tool for industrial building purposes, whereby we can potentially use these catalog steel frame members that will already have some essential information about, the usability, the end of life cycle, whether it can be used on that particular revised design of an industrial building. Again, this type of research requires that there already is a digital twin, that you already understand the nature and the capacity of those steel frame members so that they can be incorporated into the next generation of industrial buildings. And then Dr. Hamid is also looking at digital twins, although his work is more focused on roads maintenance capture data. So in this case, it's a combination of terrestrial and UAV data that is then combined to assess the road-based conditions. And Project Omicron is an EU-funded project. I think it's worth about 4.9 million. It's a collective research effort, but Dr. Hamid Reza's focus area is on actually utilizing point cloud data to generate a more accurate representation of the roads-based conditions. So it's a combination of inspection vehicles and LiDAR data, and part of the product that Cambridge is developing or co-developing here is a solution that we've previously developed called PointPix. And PointPix is a solution essentially to identify the conditions of the road based on point cloud data. So again, in this scenario, this is the use of digital twins for the purpose of maintenance of roads. And much of our research really is focusing on digitally twinning our road infrastructure. And the point of Digital Roads of Future at Cambridge is to sort of help develop the infrastructure's development to be as smart as the vehicles that drive on it, because the roads, as was mentioned this morning in the UK, we've all experienced disruptions within our roads. They've definitely would benefit from having some sort of more accurate representation of maintenance of our existing road infrastructure to reduce traffic loads and other impacts on society. Dr. Sun, his work is also focused on roads monitoring. His research work is actually more on the data science part, so it's more focused on creating more accurate representations of the structural degradation of the roads. So this is doing more sort of physics-based modeling to assess what sort of condition or predict the conditions of the roads over time. As you are aware, in the UK, we have very different climate to the Nordics and the Baltics, but nonetheless, it does degrade our roads over time, and it's something that needs to be monitored and improved in terms of our predictability on the conditions of roads. So a key thing I want to just summarize is that when I mentioned twin systems, the core concept really is to think about digital twins from a systems point of view or a systems perspective, much like the built environment is composed of complex systems within the digital, the physical realm, and the social realm itself. And as we increase in complexity, it makes sense for us as well to think about digital twins and their life cycle. So when we implement digital twins, the value that is derived from them must also justify the cost. And when we implement these digital twins, they will inevitably have their own life cycle as well that require maintenance. That information needs to be updated, but our physical structures will age at a different rate to our digital information online. The sensors we embed in our road networks may quickly become outdated and need to be replaced, but we'll still have a track record of what was there and what were the key decisions that were taken throughout the development of those roads. So we are transforming the industry as a whole and the way in which the industry is thinking about value and deriving value from digital twins. Another transformation that is required from the businesses and the industry side is also a transition in commercial models. The ability to actually share and disseminate data between different platforms is critical. We have a startup company at Cambridge that has spun out, which is trying to tackle this problem of translating different sources of data from digital twins. We all know that the interoperability is a really challenging part of digital twins, but in order for value being derived, different digital twins inevitably will have to be able to communicate with one another. And there definitely will be room in the commercial space for solutions providers to try and be able to translate that information, to try and improve accessibility to digital twins, such as a more natural way of interacting with that data. That's when you can really begin to unlock some of the value of using digital twins. So it's not only just increasing in efficiency, there's also potential to innovate and to generate new revenues and services by having those multiple digital twins be able to communicate with one another. And I do agree with the previous speaker as well that, the digital twin has to be a sort of shared representation of what really is there. And a big part of our debate over a whole year with 4 professors was actually, where does the digital twin start and end? Because you could equally say that actually when we develop those AutoCAD drawings, which we still do, don't deny that they're not being used because they are those also a digital twin representation in the life cycle? And how do we then get access and retrieve that information over time? The book in itself is more of an overview. It's more of a generic framework. You're not going to see technical details in that book. So if you are interested, have a look at our YouTube page. You may find some interesting short videos from my colleagues as well on our debate and our discussion on twin systems. And with that, I think I've come to an end, but the clicker isn't working. So I thank you, and if you have any questions, you can always contact me afterwards, and I'd be happy to answer any questions you have.
Thank you so much, Erika, for your presentation. And we will now continue with the next one, and you can go to her during the coffee break and ask everything on what's the meaning of life or something about digital twins. But thank you so much.